Jim McGregor here. Welcome to another TIRIAS cast. I'm here at SC25, Supercomputing 25. I'm here with Girish Cherussery, and he's the Vice President of AI for Micron's Cloud Business Group. And we're going to be talking about, this show is actually phenomenal. I think key topics really center around not just high performance computing, but also AI. And we don't have any of that. AI doesn't exist basically without data, and you guys control data. So tell me a little bit about, we know about HBM, but what else are you doing for HPC and AI that's really enabling these high performance solutions?
Yeah, no, Jim, super excited to be here at Supercompute. One of the things I love about Supercompute is it sets the pace for where the industry needs to be in the next 5 to 7 years. It kind of is future looking in some ways. And you said it right, HPC, AI, they're becoming more and more synonymous in some way or the other. When we think about HPC/AI, especially from a memory perspective, bandwidth, capacity, latency become the three main ingredients in the memory world. And you have different tiers of that solution. You have the high bandwidth memory, which is placed right next to the GPU or the XPU or the host, trying to do these massive parallel computing. And the next tier below that becomes more like the traditional memory, which we would be calling it the DDR memory.
Yes.
And there are different flavors of that coming out, trying to meet those bandwidth needs and capacity needs of the future. And then more interestingly now, we have a new class of memory called the SOCAMM2, which is basically using an LPDDR memory in a module form factor that goes right next to the CPU on the same AI node, or right next to the CPU inside the AI node. And we've been partnering with our folks for about 5 years working on this solution. The beauty of this solution, for example, is it provides the bandwidth, and it also provides the capacity of an LPDDR memory right next to the host. And great solution from that perspective. And then the tier beneath that is basically you start looking at CXL, which is more of a disaggregated pool of memory that you can go access that's sitting further away from the compute engine. So if you now take all of this, that's the memory portfolio, and then you tack on the storage piece that comes beneath that, you've got a full stack of all kinds of solutions that help you store the data. So there's an interesting analogy I keep telling my friends when they ask me what I'm working on, what does DRAM do? I tell them that it's a very interesting thing. Like if you can imagine I gave my kid 3 tasks to do, and they can do all 3 of them, they have to remember all 3 of them, and they have to do all 3 of them. So how they remember is very similar to how a DRAM holds that piece of information in its head in a supercomputer or in a AI computer. That's how you build the agents that help you do your job. So
I like that analogy. Unfortunately, my kids lack the storage part. They get the short-term memory, but lack the storage. So as we're looking at this, though, we also have CXL for that pooled memory, and we're starting to see an uptick in interest in CXL. Can you talk a little bit about the applications and why we're seeing that interest now?
Yeah, I think AI with its large model size and with the need for more memory capacity, you're going to begin to see a disaggregated set of memory solutions for different workloads. Kind of when we started out, AI was one big engine that required a GPU with HBM and then some x86 CPUs. And then that evolved into an ARM CPU with some memory, like an LPDDR memory. You're going to start to see that expand further out as you break down AI into prefill, decode for inference, and then training. And how you think about that is CXL in this particular case is fantastic for a large pool of memory that you need, where you don't care as much about the latency, but it's a large swath of memory that is available. So for example, if you take one of the things that we did recently was we did some work with the Northwest National Labs. And with the PNNL, we built a computer called CRETE, CRETE, where the memory and the compute is co-optimized. And the way about 2 terabytes of memory were built into this system was using CXL as the protocol for it to communicate with the host. So, and predominant application here was science and research. but you can start to kind of take that and scale it out into further applications beyond the HPC or science applications that we see today. So we are strong believers that memory is becoming a big bottleneck for us to scale AI. And as we have to think about that particular kind of solution, we have to start looking at not just one kind of memory technology, but you have to look at a swath of different solutions that basically target different applications. So if you need large capacity, you can have an MRDIMM, or you can have a DDR5 high capacity DIMMs like 512 gigabytes, 128 to 512 gigabytes. You can have a SOCAMM2 with an LPDDR, which is a module form factor. If you're looking for extreme high bandwidth, you have got the HBM. And then beneath that, you have the GDDR solutions, which also provide very high bandwidth. And if you're looking for storage solutions, we've got the 9550 NVMe storage class of storage application. So the whole pool or the whole swath of different memory solutions and storage solutions together, you're going to need all of it to service the AI market.
Well, and it's not just about, we are seeing these very large AI models, but in a lot of cases, we're seeing kind of a layered AI approach to where, you might have AI in the application, you might have AI at the system level, and you might have AI as an agent all working together in kind of that layered approach, or a mixture of experts where you're actually breaking down that large model into a bunch of smaller models to do things. So, I mean, does that all play into this strategy too?
Absolutely.
Or do we need a particular type of memory for that mixture of experts type of solution?
Right. No, I think if I just take AI, let's take inference, for example, and you can break it into prefill and decode. For large context lengths, prefill is pretty much compute bound, where you're generating your first token and it's mostly compute bound. You really need a high bandwidth memory for that particular solution? Maybe not.
No, just lots of memory to handle that data.
It's fantastic. If you have a really large context, you're going to be spending more time on the compute, less on the memory bandwidth. But as soon as you're done with your prefill stage and you go into the decode stage, now all of a sudden you get, bam, it becomes a memory bandwidth constrained world where you're a memory bound problem at this point. And that's where the HBM starts to come into play, for example, where you really need very high bandwidth, very low latency, energy efficient solutions in that particular class of solutions. And then you can kind of now take that and say, okay, I need more capacity right next to the host in a cache coherent system. Take, for example, the Grace Hopper CPU GPU combinations. Right? You have an LPDDR that's either a memory down or the SOCAMM2 that we just came out with, which is a module form factor with the CPU memory. So you get more fast memory that's sitting right close to the host where the compute's happening. With mixture of experts, even though you've kind of streamlined the application down to a set of parameters that you really want to go compute your workload on, what ends up happening is with the chain of thought reasoning models, all of this compute is again basically scaling into multiple threads. If you were to think of it as trying to come up and see which is the best solution that you should be using for your final output. And as you think about that from that angle, even though it's almost like you needed a mixture of experts for you to be able to scale your models out in the future. It's not like that actually simplified the problem. It just gave a new class of applications new life for it to continue to grow. So this thing is just going to keep growing bigger and bigger, and newer solutions are going to be needed for us to kind of continue to evolve this AI market.
Yeah, it's one of the misconceptions I get from a lot of people saying, well, we're going to keep shrinking these models, and we're going to put everything on the edge. I'm like, I don't think you really understand this. Even from a prompt, if you ask an LLM a simple question or a chatbot a simple question, it's going to give you a simple answer. When you ask it to write a paper or produce a video or to create a song, you're exploding the requirements and the compute requirements, the memory requirements, everything to be able to handle that task.
Right. And can you imagine what happens when video comes into this?
Oh, our forecast is already phenomenal.
Right.
I mean, it's ridiculous the amount of storage and memory that we're going to need. It is definitely a scale problem at this point in time.
Oh, absolutely. I mean, I love to watch my grandparents who are no more come alive through some of the video generations that AI has been able to duplicate just using their images, right? So there are some cool applications being built that I think will just continue to scale. So that's on the entertainment side or more on the human side of things. You take the medical field, that's going at a completely different phase, and you've got drug discoveries happening because of the new tools that you have at your hand to come up with new compounds that help you innovate and come up with new pharmaceutical drugs to help cure a lot of diseases. So, I mean, this landscape is just at its very nascent, early stages in my mind.
I have one other key question here, and this really came up at FMS, and that was the fact that power consumption is becoming so critical. And Micron's done a phenomenal job, both on the NAND and the DRAM side, the memory and the flash side, to be able to produce some of the most efficient solutions on some of the most advanced process technologies. Right. So, I mean, how important are you seeing that with your customers now?
Oh, absolutely the most important thing today, right? I mean, when you start looking at gigawatts of data center, they're completely power constrained, right? You can get enough power online for these data centers to grow. You mentioned, process node scaling. The fundamental in the DRAM and the NAND world for us is scaling. So we recently went from a 1 beta node to a 1 gamma that is in production today. So scaling helps us improve the power efficiency of the solution. On top of it, when you layer in the architectural innovations that need to happen, for example, our HBM3E is about 30% more power efficient than its next best competitor. Going into HBM4, we further lower that power efficiency by another 20%. So, that's on the HBM side. Now you look at SOCAMM, for example, you're using an LPDDR component, which is already very power efficient, to basically bring in additional power efficiency into the memory solution. So it's super important, and we are very focused on ensuring that we're not only delivering the performance, but we're delivering it in a very power efficient manner, because systems are going to be very, very constrained in the future in terms of how much power can be burnt by the memory or the subsystem, because now we're talking about 300 kilowatts to a megawatt of rack. And these are not easy to cool. So it's not just the power delivery, it's also the thermal management of this. So we are extremely focused on this space to make sure that the future AI architectures can continue to scale and deliver the performance that they so need.
That's great. Thank you very much.
Thank you.